Good afternoon, everybody. I'm Mila Pola. I'm with the Library and Archives here at Coastal Harbor Laboratory. And this event is organized by the Center for Humanities and the History of Modern Biology at Coastal Harbor Laboratory. Thank you very much for coming to this event. And I would like to introduce our speaker. I'm delighted to introduce you, Dan Nicholson, who is Assistant Professor of Philosophy at George Mason University. He's also a Sidney Brenner Scholar here at Coastal Harbor Laboratory and a Mercator Fellow at Ruhr Universität Bochum. Yes, Dan's background is in philosophy and molecular and cellular biology. One of the goals of his work is to revive an organism-centered philosophy of biology, overcoming the limitations imposed in mechanicist and deductionist approaches of late 20th century of biology. I have to say a few words about our Sidney Brenner Research Scholarship that was endowed by famous and well-loved here Sidney Brenner, and his postdoc at that time, Philip Gallet. And one of the criteria of this fellowship, which is very prestigious, is to give a talk about the work supported by the scholarship, this funds. So welcome, Dan, and I'm looking forward, as we all, to listen to your talk.
All right, thank you very much, Nina, for that very nice introduction. It's a real pleasure for me to be here back at Coastal Harbor Laboratory. I spent a few weeks last summer doing some archival research, looking at the personal notes of a number of major towering figures of molecular biology, including James Watson, basically researching the reception and interpretation of this very, very famous book, What is Life? A Physical Aspect of the Living Cell, published in 1944 by the great physicist Schrödinger, based on a series of lectures delivered the year before. This whole project began really when we were commemorating the 75th anniversary of the publication of the book. That was back in 2018. I thought, well, maybe I could write something about the legacy of the book. And when I started looking more closely at the origins that led to the writing of the book, and also how it was received by different generations of molecular biologists, I realized that a simple commentary piece will not do it any justice. And so basically I dived into this hole, which I haven't yet been able to escape from, where I've been basically reading everything that I could find on the book, on basically all the references to the book in the work of molecular biologists to understand better the relevance of reception. And I realized that even though it's a very, very well-known book, it's a classic, everyone's heard of it, there is actually still a lot that one can say about the book. Not everything has been said. In fact, this was dawned on me that there was an interesting story that one can tell, which is a little different from the received view that we have of how this book came about and its relevance. So this is what I'm going to be presenting you today. Essentially, it's going to be a talk based on a little book that I'm writing for. This works. Does it work? I don't seem to be able to move.
We don't have any
change slides for some reason.
Yes.
Is it working? Okay. Yeah. So this is just for bringing Google books. This will come out next year with Cambridge University Press. It'll be a short book, and it'll probably be as long as the original book. And I'm going to be presenting to you some of the highlights of that. I won't have time to go through everything, okay? But to give you a taste of what it is that I think is still worth saying about this book, almost 80 years after it was originally published, okay? Okay, so let's just begin from, as I said, it's supposed to start in August, to appear in August 2023. So let's begin with the actual lectures that gave rise to the book. This is the poster from the Dublin archives, the Dublin Institute of Advanced Studies, the original poster that was printed, a very humble one. When you probably can't read it from where you're sitting, it's basically just announcing that the great Schrödinger was going to be giving these lectures February 1943. So I don't really have time to go over Schrödinger's life. It's a very fascinating life story because originally, of course, he was born in Vienna, had to eventually ended up taking over Max Planck's chair of theoretical physics in Berlin, but then he renounced, even though he was not a Jew, he renounced his position when but it didn't really fit very well in Oxford college life, and he was longing to return home, so he did, but at really the worst possible time. 1936, he returned to Austria, to Graz, and 2 years later, of course, the Anschluss happened. Austria no longer ceased to exist in part of Germany, and so he had to disappear and rush out of the country before his passport was confiscated. And Herman de Valera, the Prime Minister of Ireland at the time, was able to basically create an Institute for Advanced Studies for him to be able to move there, modeled on the Institute for Advanced Studies in Princeton, where Einstein had moved not long before. So actually, the one in Dublin is the second oldest Institute for Advanced Studies, and there he was able to work peacefully and focus on. He was already in his 50s, but one of the things that he had to do as part of this having this role is that every year he was supposed to give these lectures, these public lectures. Okay, in 1943 he decided to give these lectures on this question, what is life? Okay, this is what the poster shows, and well, just to say, the lectures were a total success. There were, in fact, so many people came that he had to repeat the lectures. So there was supposed to be scheduled on Fridays, and he had to repeat them on the following Mondays. And in correspondence, Schrödinger's wife, Marie, writes to Mark Spon saying that it was like an opera premiere. And it was all the intelligentsia of Dublin were there. The Irish Times ran a piece on the lectures. So it was a huge success. And Schrödinger knew from the beginning that he was going to want to write up these lectures in the form of a book, which came out the following year in December 1944. There's a wonderful, very interesting story about the publication of the book that I don't have time to go into. Well, I'll basically very briefly summarize it. Originally, Schrödinger had found an Irish publisher, but at the last minute, just when he was going through the proofs, Schrödinger decided to add an epilogue on free will and indeterminism, which upset the Irish publishers because it was suggesting, it was appealing to Vedanta philosophy, and it was sort of going against sort of the Catholic ideas, were very much part of the mindset of that time, and so he had to find another publisher, which he did with Cambridge University Press. So that is the first edition of the book, as when it eventually came out. And you probably can't see it. There's a little subtitle there. It says the physicist's approach to the subject, with an epilogue on determinism of free will, which Schrödinger was very keen to add. And I'll explain why that is. So the book was been a total success. I just spent some time online Googling, looking for images of the book, and I found all these covers from the book in its translations, right? There's loads that's been translated to many different languages, gone through lots of different editions, and it's a classic. I mean, everyone knows about the book. And one of the reasons why it's become so famous, and it's become, I would say, perhaps certainly one of the most influential and famous books, science books of the 20th century, but the reason why it's become so sort of legendary in the story of molecular biology is that most of the founders of molecular biology actually mentioned at some point that they were influenced, they read Schrödinger, What is Life, and they were influenced to turn to examine the molecular structure of the gene as a consequence of having read what Schrödinger had to say about life. Okay, and so you actually quite easily are able to find all these wonderful quotes from very sort of all these sort of founding fathers of the field. So here's Maurice Wilkins. This is taken from his Nobel acceptance speech, where he says, well, during the war, I took part in making the atomic bomb. When the war was ending, I, like many others, cast around for a new field of research, partly on account of the bomb. I had lost some interest in physics. I was therefore very interested when I read Schrödinger's book, What is Life? And was struck by the concept of a highly complex structure which controlled living processes. Research on such matters seemed more ambitious than solid-state physics, and it encouraged me to move into biology. That's 1963. You have James Watson, sitting here in the audience, on a number of occasions has mentioned the influence of Schrödinger's book. I like this one particularly. When I came back to the University of Chicago, I spotted the tiny book, What is Life? In that little gem, Schrödinger said that the essence of life was the gene. Up until then, I was interested in birds, but then I thought, well, if the gene is the essence of life, I want to know more about it. And that was fateful, because otherwise I would have spent my life studying birds and no one would have heard of it. So, you know, it's a very clear sort of demonstration or recognition of influence on the part of Schrödinger. But there are many. Francis Crick, speaking more collectively, not necessarily personally here, but although in other occasions he has admitted personally to being influenced, but here talking more generally, he says, of those who came into the subject just after the war, Schrödinger's What is Life seems to have been particularly influential. The book was extremely well written and conveyed in an exciting way the idea that in biology, molecular explanations were not only going to be extremely important, but they were also around the corner. This had been said before, but Schrödinger's book was very timely and attracted people who might otherwise not have entered biology at all. And here's one more from Gunther Stent, one of the members of Delbruck's Space Group, writing sort of in a historical vein, having one of the founding fathers of the new physics put the question, what is life, provided for physicists an authoritative confrontation with a fundamental problem worthy of their metal. In thus stirring up the passions of his audience, Schrödinger's book became a kind of Uncle Tom's Cabin of the revolution in biology that, when the dust had cleared, left molecular biology as slaves. Okay, so you can't have any more clear, any clearer sort of recognition of the importance of this book, and I could mention a number of others who similarly written about the influence of Schrödinger, Seymour Benzer, Brenner, a number of others. Okay, but I think these suffice to make that point. This is a wonderful letter that can be found in the archives again in Dublin. It's a letter written by Francis Crick, addressed to Schrödinger, sent to Schrödinger. And I believe it was sent a couple of weeks after the publication of the papers in Nature showing the double helix structure of DNA. It's August 1953. And Crick writes, Dear Professor Schrödinger, Watson and I were once discussing how we came to enter the field of molecular biology. And we discovered that we had both been influenced by your little book, What is Life? We thought you might be interested in the enclosed reprints. So you will see, I imagine the reprints were obviously the papers with the double helical structure of DNA. You will see that it looks as though your term aperiodic crystal is going to be a very apt one. So again, very interesting historical document here showing the influence, the massive influence, the intellectual influence that Schrödinger's book exerted on this generation of molecular biologists. And so what you find today, we fast forward back to the present, is when the 75th anniversary was being commemorated, all the major journals made sure that they published a piece commemorating it. So this is the one that came out this is the one in Nature, this is the one in Science, and there was even a big conference organized in Dublin in Schrödinger 75. It's a bit of an odd title because obviously Schrödinger wasn't 75. It's the publication of the book that is 75 years old. It's a bit weird. The other weird is that the conference and all of the, this is a who's who with lots of Nobel laureates, speaking, is that actually very few, if any, actually discussed the book at all. It was more like, well, just discuss the contents of the book. And in fact, if you look at these commemoration pieces, the same thing, right? So you hear again and again what I've shown you so far, right? That the book influenced others. We don't actually get to see, you don't get any sort of information about what the book was trying to argue. Like you don't get any sense of the argument. And I noticed that this was a common trend, so that basically this is a book that maybe like Darwin's Origin, people like to cite, but it's not as widely read as it is cited, okay? So this got me thinking that it was a little weird that even though you're showing this face is plastered everywhere, for example, this conference was organized to talk about the future of biology, okay, with no real discussion of the argument. And if you go back 25 years in time to the commemoration of the 50th anniversary of the book, another book came out at that time, What is Life the Next 50 Years, published also with Cambridge University Press, featuring a very, distinguished roster of speakers. You probably can't see, but I can
point them out to you. You have Stephen Jay Gould, you've got John Maynard Smith, Lewis Walcott, Stuart Kaufman, you have Roger Penrose, Leslie Orgel. So you have, again, a very interesting sort of roster of speakers. But again, very little discussion, if any, about the book, about the argument. And this is kind of odd because the book is a short book. You can read it in an afternoon. And one of the reviewers famously said, you can read it in an afternoon and you won't forget it in a lifetime. And yet, as I said, you don't get to see much of what the book is just trying to argue. So let's try then to work out what it is that the book is saying. Okay. So these are the sort of the sound bites that everybody knows. If you stop a molecular biologist in the street and you ask them, you shake them and you say, tell me what you know about what it's like, they're likely to tell you any combination of these three things. Okay, these are the three, what are taken to be the three take-home lessons from the book. The first one is that the hereditary substance is an aperiodic crystal with a code script for development. The second one is that organisms feed on negative entropy to comply with the second law of thermodynamics. And the third one is that the study of living matter is likely to prompt the discovery of new laws of physics. Okay. So if you didn't know anything else and you took the book, you might be expecting that the book discusses each of these three things in more or less equal measure. But that's really not the case. So if you look at the book, okay, you open up the book, one of these wonderful old books that have this analytic table of contents that summarize the chapters. Fortunately, you can't see it because the screen is too small. But if you look at this is the book, as I say, less than 100 pages. And if you look at where Schrödinger is talking about negative entropy, it's actually just one half of one chapter. Not only that, but when he starts talking about thermodynamics and negative entropy, he actually says, let's forget for a moment everything we've been talking about until now, okay, and discuss the bearing of entropy. Okay, so it's not even part of the argument that Schrödinger is presenting in the book. Okay, he says on page 73, 79, these are the 6 pages devoted to this discussion of how organisms comply with the second law of thermodynamics. It's really kind of detached from the rest of the argument. Okay? What about the third point? One about new laws of physics. Where does that come up? Well, that's even more interesting because it's actually just one section of the final chapter, where Schrödinger says, at the beginning of the chapter, living matter, while not eluding the laws of physics, is likely to involve other laws of physics, which you will know. Okay. So actually, most of the argument, or actually no, most of the book is devoted to work to developing that first one, that first sort of idea, that first claim. Okay, so that's the one we need to focus on if you want to understand what the book is about. The hereditary substance is an aperiodic crystal with a code script for development. Okay, so let's work out what that means. So the book, What is Life, isn't actually an attempt to answer the question, what is life? Okay, it's a sort of misnomer. The question it's trying to address is, what is the nature of biological order? Okay, and this is how Schrödinger proceeds. The first chapter of the book is called The Classical Physicist Approach to the Subject. And in this chapter, he's going to tell his readers how physicists think about order. Okay, and how do physicists think about order? Well, he says physics tells us that atoms, individual atoms, are incapable of displaying regularly behavior. Okay, why? Because they're subject to the stochastic effects of thermal agitation at any temperature of absolute zero. Brownian motion, as it's known, right? Because of Brownian motion, individual molecules are too disorderly to exhibit any sort of regular behavior. Okay, so what that means is that the laws that physicists work with have to be necessarily statistical in nature. Why? Because the order and the regularity that physicists identify in nature can only emerge upon considerations of a huge numbers of atoms, molecules, particles, or whatever, that only when considered collectively display patterns of order, as described by the law of large numbers. Okay, this is fairly well known stuff. Not all laws of physics are like this, mind you. A good exception is gravity. Okay, in fact, Max Planck distinguished between dynamical laws like gravity and statistical laws, but for the most part, most laws of physics are of this nature, okay? Which means that when a physicist is trying to understand order, he or she is going to try to work it, try to make sense of it by thinking of it statistically, okay? He calls this the order from disorder principle at work in physics, okay? And of course, that's a reference to the work of people like Boltzmann, who was a huge influence on Schrödinger. He gives a number of examples to illustrate how order emerges in physics. These are taken from the book. Okay, this one is the first one is sinking fog, right? That when taken collectively seems to be moving in one direction, but if you take one droplet individually, it has sort of this random walk, which is not ordered. Okay, if you take it individually, no order. If you take it collectively, order emerges. He gives a number of other examples, right? Diffusion. If you trace the trajectory of a particle, no order, collectively you can make certain predictions, and paramagnetism and so on. Okay. So what about life? That's so okay for physics. What about life? Well, Schrödinger says, well, a naive physicist, he says, might think it trivially true that the order of life has to be also based on this sort of patterns of behavior exhibited by large ensembles of molecules. All this was very orderly, right? So a naive physicist who didn't know any biology could be excused to think, right, if he thought that the order that life manifests is also statistical. But then Schrödinger says, not only is that not trivially true, it's actually wrong, okay? So in chapter 2, called The Hereditary Mechanism, has this subtitle, The Classical Physicist Expectation, which I just told you about, far from being trivial is wrong. Okay, so the plot thickens. What is the order of that biology shows us? Well, the order that biology shows us seems to be essentially determined by its genes, Schrödinger says. Schrödinger's writing in 1943, okay, and he has read the literature on genetics at the time and seems to be convinced of this idea, right? That the order of life is determined by its genes. Now, we know, and this is of course even before genes were recognized as DNA, when most people still thought that genes were proteins, that genes are actually quite small. They're far too small for the law of large numbers to apply, okay? So we've got a problem here. We can't appeal to the law of large numbers to make sense of the order of life because the sources of order in life are too small for that to happen. Since genes are so small, they should not be able to reliably code for heritable traits, given that they're firmly in the grip of thermal agitation. Because they're small, they should be exposed to this thermal agitation, so they should not be able to exhibit any order. And yet we know that they are extremely orderly and that they are remarkably stable with a durability, Schrödinger says, this is a direct quote from the book, or permanence that borders upon the miraculous, Schrödinger says. Okay? The entire book can be understood as an attempt by Schrödinger to solve this paradox. Okay, the whole book is essentially trying to solve this paradox. How do we reconcile the small size of genes with their extraordinary stability in the face of constant stochastic perturbations? Okay, he gives a very nice example of the stability of genes. As it would be an easy, he mentions the House of Habsburgs, the royal family of the Austrian Empire that for 400 years exhibited this malformation in the jawline, right? And you can find, and when you look at the portraits of the Habsburgs from the 16th century to the 19th century, these are some examples of the both Austrian and Spanish branches of the Habsburg family, where you have this protuberation. This is a genetic trait, right? And so Schrödinger says, well, look at this, right? This is a trait that has been sufficiently permanent to have survived, 400 years, right? And yet we know it has a molecular basis. So how is that even possible? How do we make sense of this? Okay. So how does Schrödinger resolve this paradox in the book? Well, he reasons, and this is all sort of armchair theorizing by using his considerable intellectual resources. He reasons that genetic material has to be as solid, right? Has to have the structure of a solid, even though it's an individual molecule, right? It has to have a solid state structure of a crystal, it says, because only then would it be able to withstand the disruptive effects of ground motion, but not just any crystal, because it needs to be able to encode information. It doesn't use the language of information because that comes into biology later. In fact, I think Watson and Crick's paper is the first sort of proper use of the notion of genetic information. So we're talking this is a decade earlier, right? So he doesn't talk about information, but he's talking about how he needs to code, needs to be able to have the sort of four-dimensional pattern of the organism, right? So it has to be aperiodic. Within it, the code script, this is the term that he used. Again, this is the first time that the term code is used in this context, okay? So Schrödinger, of course, this is written during the war period, so it makes sense. There's a lot of coding and code talk in the air, and so he uses this language, and it also, of course, potential interaction. And so he said, well, unlike physics, where you have this order from disorder, in biology, we seem to have a completely different situation. We've got this order from order principle at work, right? where the order that you find in microscopic organisms is already there in the individual molecules that code it. You've got this amplification of pre-existing order. So that's the pre-formationist argument, okay? And he says you don't find that in physics, but you do find that in machines. You think about the design of a machine, right? You've got a blueprint, and then the machine is basically assembled on the basis of a blueprint. You also have this sort of order from order principle, okay? Which is also why Schrödinger thinks that this machine analogy with the organisms is appropriate, right? Because both are based on this order from order principle. Right? So as he says, so this is towards the end of the book, in one of the last pages, the clue to the understanding of life is that it is based on a pure mechanism, a clockwork that also hinges upon a solid, the aperiodic crystal forming the hereditary substance, largely withdrawn from the disorder of heat motion. He says, genes seem to work as if they were absolute zero because they don't seem to be affected by Brenner motion, right? He talks in these terms. So this is Schrödinger theorizing and trying to make sense of the stability, the miraculous stability of biological order. Okay, so let's just have a look at what happened with this idea of the order from order principle with the benefit of 75 years of hindsight. Okay, so we think about what Schrödinger is saying here. He's talking about this hereditary code script, and often in the literature, people seem to suggest that this is the forerunner of the genetic code, right? Because you've got this language of code. But this is actually quite problematic because Schrödinger doesn't seem to be talking, or doesn't actually about the translation of one language into another in the way that the genetic code does. So it's not really a cipher like the genetic code, but rather Schrödinger seems to be talking about the code script as a sort of plan for development. The way we talk about the highway code, for example. So we use the code in that context. Okay, and it seems clear when you think about it that the actual novelty in this notion of the code script has not much to do with this idea of genetic code, but actually more with the idea that there is a plan for development, right? And of course that became sort of articulated later, 15 years later, simultaneously by Ernst Mayr and by François Jacob and Jacques Monod in 1961 with the concept of the genetic program, right? So you can think of the genetic program as essentially Schrödinger's code script. That's a better way of thinking about the legacy of the genetic code. As such, it is subject to many of the same problems, empirical problems, that with the benefit, again, of 75 years of further research, we have found with the original notion of the genetic program, okay? So these are just three ideas or three theses that seem to be subsumed within the notion of the genetic program. Neo-preformationism, the idea that developmental information is fully encoded in the genes. Genetic animism, the idea that genes not only have the information, but they can initiate, direct, and control developmental processes. And also this notion of developmental computability, which is that if you have complete knowledge of how genes interact, you'll be able to compute the embryo, okay? Now, all of these ideas are actually prefigured in the way Schrödinger uses the term code script. So what I've done here, I've just taken the quotations from What Is Life where the notion of code script comes up, and I've been able to essentially put them according to the thesis that they're defending. So I won't go through this in detail, but it just shows that when you look at how Schrödinger used the term, you have a defense of these three theses that I've just shown to you. Neo-preformationism, genetic animism, right? The law code and executive power, architect's plan and builder's craft, right? And this idea also of computability, which people like Lewis Wolpert then wrote about in the 90s. It's already there. I mean, he talks about Laplace's demon, right? If you had knowledge of all the causal connections immediately open, one can tell the structure whether the egg would develop into any of these things. It's in the final quote here. Okay. So of course we can say now that Schrödinger was right to suggest that there is an order from order principle at work in morphogenesis, and of course that also that this order is intimately connected with the hereditary substance, but it seems clear also that he was wrong to want to localize in that hereditary substance all the information required to specify the organism, because of course that ignores the influence of the environment effects, right? It was even more wrong to think that one can invest the DNA with the causal power to initiate, control, and direct development. These are things that the cell or the organism does as a system, right? DNA really does nothing alone. It is the cell as a whole that has activity. In fact, the very stability that so much fascinated Schrödinger of DNA is not something that is intrinsic to the molecule of DNA. It's an accomplishment, right? It's an activity that is constantly accomplished by the cell through self-repair mechanisms. right, which are ensuring that DNA, when it is replicated, it doesn't accrue errors, right? So in a way, you can think that the paradox, the puzzle Schrödinger can be solved or has been solved by attending to the details of molecular biology. Okay, and of course we got the other issue, of course, that you have other forms of order that are not found in the genes, right? You've got epigenetic inheritance. I won't go into that, but that could be something that one could also say, right? I'm going to shift gears a little bit for the second half of my talk and talk a little bit about the legacy of the book and talk about how it's been received. Okay, so something quite interesting happened in the 1980s. So I've shown you some quotes, right, from Watson, from Wilkins, from Crick, many others, from the 60s, confessing to having been, completely blown away by Schrödinger and having decided to move into the field that became molecular biology as a result of reading it. In the 80s, you have, in 1987, the publication of a book that was supposed to sort of commemorate the centenary of Schrödinger's birth. Okay, and in that book, Linus Pauling and who was the other person? Linus Pauling and Max Perutz were invited, okay, to write about Schrödinger's contribution to biology, and they had very, very sort of surprisingly negative things to say. So, as a consequence of this, sorry, let me just show you those two quotes first. So, this is what Perutz is saying about the book. A close study. This is 1987. A close study of what is life has shown me that what was true in this book was not original, and most of what was original was known not to be true, even when the book was written. So pretty damning. The book. Linus Pauling, who had actually worked with Schrödinger as a theoretical chemist. Again, very critical. When I first read What is Life over 40 years ago, I was disappointed. It was and still is my opinion that Schrödinger made no contribution to our understanding of life. He then goes on to say, of course, that by proposing his wave equation, he provided the foundation for chemistry, and by providing the foundation for chemistry, he provided the foundation for biology. But with regards to the book itself, he says that seems to have had no influence. And this excited a number of historians of biology in the 1980s to want to suggest that we perhaps should be a little bit careful and not take scientists at their word when they put the historian's hat on and they start talk autobiographically about influences, right? And so the consensus, and this is the consensus that we still have today, right, of the book. If you ask any professional historian of biology today, what they will tell you is that the book was influential because it gave credibility to a new scientific field by associating it with one of the great, thinkers of the 20th century. But that the book itself, the content of the book had no value. It was only, so as many historians put it, the importance of What is Life was only recognized retrospectively to give legitimacy to the new biology by associating it with the intellectual authority of a great physicist. It conveyed excitement, okay, about this new field, but nothing about what Schrödinger actually said, these historians argue, actually made a difference. Okay, I think this is why many people no longer read the book, really. It's because it seems to be the case, it seems to be a consensus, which I'm now, of course, going to debunk or try to, that the actual content of the book has played no role in the development of molecular biology. And one of the reasons they say this also is because all the quotes I had at the beginning, they're not from from the early 50s, they're actually from the early 60s. This is the time when molecular biology has been established, and what's happening is you have the first narrative constructed of the history of the field. And it is when these narratives are being constructed that Schrödinger's name comes up. Okay, so the historians are thinking there's something wrong about this, right? If it was really so influential, that should have been there from the very beginning. Okay, not 15 years later. And also, maybe you shouldn't trust scientists to tell history. You need professional historians that are trained, right? This is one claim that something like. So I'm going to try to show you that this is a very problematic consensus. Okay. And I'm going to do that by trying to show you that the arguments, the way that Schrödinger thinks about life, actually did have an influence in setting the agenda for molecular biology. Okay, and when I think about the legacy of the book, one of the things that really, I think, stand out for me is that it provided sort of a justification for the dismissal of stochasticity in the examination of molecular processes in the cell. Okay, so let's see how that works. So if you remember, the argument that Schrödinger presents is that the source of all cellular order is in this fixed solid-state crystal structure of the genetic material. And that is what renders it impervious to the stochastic forces. That's what Schrödinger says, okay? Now, obviously, right, this follows directly from Schrödinger's position. That order that is encoded in the crystal has to be somehow reliably transmitted, right, to the rest of the components, especially to the protein, so that these can individually express this order through their functions in a way also that similarly eludes or overcomes this raging Brownian storm of the molecular wheel. Okay. So what I want to suggest, and this is my working hypothesis, okay, is that the influence of this idea, right, that this order, this crystal solid state order has to be transmitted by these other molecules, granted molecular biologists for several decades this license to not have to worry about the effects of stochasticity on subcellular processes, allowing them instead to focus on the structure of macromolecules, appealing to methods like X-ray crystallography, to focus on structure and assume that function follows from structure, drawing attention to the crystal-like rigidity, which of course is a trend, right? When you read molecular biology in much of the last the last century, emphasizing function specificity and ignoring destabilizing influences of the microscopic environment. I think that this is very much the way you find molecular biology being presented in textbooks, and I think it's a consequence, at least partly, of this view of life that Schrödinger puts forward. It also is, I think, lies at the heart of representations that you find today, such as this one of the sea urchin development. This is developed by Eric Davison and colleagues at Caltech. So you've got these gene regulatory networks, which are deliberately presented like circuitry, okay, like solid state. Like if it was all solid, and you have wires, and of course there is no wiring, there is no solid state. Okay, the milieu of the cell is a dynamic stochastic, and yet we have representation after representation in textbooks, in review articles, in classes, in research papers, showing the cell and what's going on in the cell in this very sort of engineering mechanistic way. Okay, and what I'm suggesting, right, is that the reason why this is presented this way, and of course this is not an accident, has to do with the sort of view which I think Schrödinger was prominently proposing. Okay, these are all examples of metabolic pathways. Now, of course, the problem with these sort of representations, which we're all familiar with, is that if you look carefully, empirically, experimentally at what's going on, and you analyze what each of these proteins and these networks are actually doing, what you find is that they're engaged in many more interactions with many more binding partners, right? You don't have this clean one-to-one sort of relationship, right? This is what happens are things like this. This is what the researchers presented this called a horror graph, where everything does everything to everything, where you have in black the textbook representation of interactions for proteins, and the green and red show actual empirical, empirically observed cross signalings happening, right? So actually, what's actually going on in the cell is likely to be infinitely more complex than these sort of representations show. Okay, we're finally coming to realize this. Okay, and I think that the reason why there's a lot of resistance to thinking in that way, I think, has to do with the legacy of Schrödinger's work. That's what I want to argue. Now, you may be thinking this seems to be a little bit of a stretch to want to sort of attach all of this to Schrödinger. Okay, well, let me give you a concrete example, something I found in the archives, sadly not here, but in the Institut Pasteur in Paris. Okay, looking through the archives of Jacques Monod. What I found, interestingly, is that reading what his life led Monod in the 1950s already to shift from a statistical and non-deterministic view of biological regularities to one that reflects a static clockwork position. So Monod, early in his life, was interested in bacterial growth and had a statistical view of war, interesting, okay, which he then moved completely away from. And by the time he wrote Chance and Necessity in 1970, this very well-known sort of manifesto for molecular biology, he had embraced completely that Schrödingerian view. Now, Schrödinger is not even cited in Chance and Necessity, but if you look at the archives, what I found in these lecture notes from a lecture he gave in 1957, this, which is I think very telling. This is typed by Monod himself. This is an unpublished work. He says these are his lecture notes. The whole trend of modern molecular biology, he's writing in 1957, makes it every day clearer that structural stability and rigidity, rather than dynamicity, are the most essential and characteristic properties of the typical cellular macromolecules, he says. And then he says, Schrödinger, with the insight of genius, had perceived this as a necessary attribute of hereditary materials, exactly what I've shown you when I presented the argument about order, okay? The validity of this view is now beautifully demonstrated for DNA, okay? But it's not limited to DNA. I mean, he has Schrödinger in the margin here again, right? It's now also found that RNA is also similarly stable, and the same is also true for protein. What is Monod saying? As far back as 57, he's saying that view that Schrödinger thought was necessary to think about hereditary material, we have to sort of transpose that to how we think about RNA and how we think about proteins. Okay, so I think this seems a fairly very interesting find here to see him talking in this way. This is a really nice quotation where he's talking about the ribosome. Okay, he says the protein synthesizing process appears to work with very high precision, and we don't need to worry about heterogeneity due to errors and blah blah blah. Putting it otherwise, even in the formation of a large complex molecule like a protein, the synthesizing system, the ribosome, appears to work mechanically like a clock or a precision machine tool rather than statistically. And he says, like what? And he puts in parentheses Schrödinger. He doesn't know what to say, but he has that as a note to himself for when he delivers the lecture. Now, what's interesting about this is that this is the view from 1958. And the view that we have today, this is, for example, a paper from 2012, is essentially the diametrically opposed view of how ribosomes work. Okay? We've essentially had to unlearn what we thought we knew about how macromolecular structures like ribosomes actually work. Okay, discovering that actually most of the movements that ribosomes perform are not related to their function. Okay, and that these sort of visual, sort of virtual movies can be very misleading. Peter Moore at Yale says, well, structure-based movies, those that are based on snapshots of structures of ribosomes using cryo-EM, actively invite viewers to think the ribosome works like a clock or a machine for making candy bars. And it's really no help that macromolecules are commonly called molecular machines. The use of the word machine in this context is pernicious because the implication that the functional properties of macromolecules can be explained mechanically. Okay, what it's essentially saying is that if you want to understand what ribosomes are doing, you need to understand it in the context of the stochastic milieu in which the ribosome finds itself. And you're not going to have this simple sort of toy mechanical view where you have simple sort of structure-function relationships, okay? Okay, so let me just move on now to the final part of my talk. I want to now suggest that what I've said and the things I've suggested that Schrödinger has to answer for actually, you know, okay, what I want to do essentially is anticipate an objection that you may have and say, well, you know, it's all very well now, 2022, to complain about Schrödinger, who was not even a biologist, writing in 1943 about things he got wrong. Okay, well, let's see if it really is, if that is the case. I'm going to try and show that it's not unfair. Okay, so I've essentially just criticized two ideas that are at the heart of what is life. The first is this genocentrism, right? Where all order is rooted in the genes, and the genes are the sort of the alpha and omega here. You don't need to concern yourself with anything else. It's all coming from the genes. Okay, and the other thing I've said is that this view has led to a sort of dismissal of stochasticity. Okay, now, are we blaming Schrödinger here for not knowing the future? Are these unfair criticisms posed with the benefit of hindsight? I'm going to say no. And the reason why I'm going to say no is because Schrödinger did not have to argue in this way. Okay, the genesis of the book, which I'm going to go into now, shows that Schrödinger made a number of decisions, deliberate decisions, to end up arguing the way he did. Okay, so let's have a look then at the origins of the book. So again, a number of people have written about this. So, for example, so we need to ask ourselves this question: why did Schrödinger, a physicist, 56-year-old physicist, decided to turn his attention to biology in 1943 when he was asked to do this lecture? So his biographer, Walter Moore, says, well, his father, Rudolf Schrödinger, was a botanist. So he's had a sort of interest. He read Origin of Species when he was a teenager. He had a sort of long-standing interest in biology all his life. Okay, and that's why he eventually returned to this topic. Historians like Lily Kay and Evelyn Fox Keller have suggested that it has to do with this book that he read while still an undergraduate student in Vienna by Richard Solomon called The Meme as a Conservation Principle, which had to do with this notion of cellular memory, very, very speculative, as a now forgotten book. And that if you think about it, DNA is exactly what that DNA is providing this idea of, providing a naturalistic explanation, as philosophers like to say, of cellular memory. So maybe that's the reason why he was interested. Stephen Jay Gould, in the contribution to the volume that I showed you at the beginning of the talk, suggested that maybe Schrödinger was just part of this Viennese tradition of having this sort of systematic view of nature, and that he wanted to bring biology under the laws of physics, as it were. One of his students, Simons, he just simply said, look, Schrödinger was a Renaissance man. He had an extremely wide range of interests beyond physics, and so again, we shouldn't be surprised, right? That one of the topics he did write a book about the Greeks. He wrote books of poetry. He wrote on all kinds of topics. So why should we be so surprised that he wrote about biology? Now, I think that none of these arguments are convincing. Okay, so I want to give you my own hypothesis of why it is that Schrödinger wrote this. Okay, and I think what I think is the case is that one cannot understand what Schrödinger is up to when he's looking at the cell if you don't understand what he was doing or his context in physics. Okay, if you don't understand the debates that he was engaged in with his physical contemporaries, it is very difficult to make sense of what he's up to in biology. Okay. He was, of course, a prominent figure in debates on quantum mechanics specifically during the interwar period. And the most salient thing about Schrödinger is that he was at odds with almost every other physicist, with the exception of Einstein, and of course, the older generation like Planck and all that. But he was at odds with Bohr, he was at odds with Heisenberg, he was at odds with Born, because he refused to accept this Copenhagen interpretation of quantum mechanics. Okay, his wave mechanics was deterministic, and he never felt that the Copenhagen interpretation that became orthodox was the final story, like Einstein. Okay, Schrödinger and Einstein share that. Okay, I've already said that. So he never accepted this increasingly solid orthodoxy, which led him to become increasingly progressively marginalized already in the 1930s from the physical orthodoxy of this day. These are just some amusing quotations that I have to show you how virulent the disagreements were between people like students of Bohr and Schrödinger. This is Heisenberg writing in correspondence. The more I ponder the physical part of Schrödinger's theory, the more abhorrent I find it. What Schrödinger writes about the visuality of his theory, I find it correct. This is, of course, a translation from the German, but I think it's a fairly faithful translation. Schrödinger, now the damn Göttingen people, of course referring to Heisenberg, Born, Jordan, the fans of matrix mechanics, are using my beautiful wave mechanics to compute their shitty little matrix elements. Excuse pardon my language, but this is a direct quotation. If we're going to have to stick to these damn quantum jumps, then I regret that I ever had anything to do with quantum theory. This is Schrödinger, okay, writing about his dissatisfaction with the interpretation of the pervaded. In fact, his very famous paper, in fact, his last major paper on quantum mechanics, published in 1935, The Current State of Quantum Mechanics, where he famously proposes his cat thought experiment, was intended as a reductio ad absurdum. He was intended to show that if you take seriously the idea, the interpretation that Bohr is putting forward, you would have to conclude, right, that the cat in the box would be in a state of superposition, both stating alive until you open the box. Naturally, doesn't make any sense. Instead of convincing people that there was something wrong with the interpretation, they interpreted this thought experiment became the sort of poster boy of the whole interpretation. It made it cool. So again, this is kind of tragic when you think about Schrödinger today. He's remembered for a thought experiment that he hoped would actually debunk the interpretation that is now known for. Right. So why is this important? It's important because Schrödinger actually never wavered in his commitment to a deterministic view of nature, and this is a consequence of his influence by Boltzmann, even though Boltzmann committed suicide the summer before Schrödinger started his studies at Vienna in 1907. He was taught by Boltzmann's colleagues and students, Exner and Assenhall. This is a wonderful quote from Schrödinger's autobiographical reminiscences, where he says, "The old Vienna Institute, which had just mourned the tragic loss of Ludwig Boltzmann, the building where Hasselhoff and Franz Exner carried on their work, gave me a direct insight into the ideas which had been formulated by that great mind. His line of thought may be called my first love in science. No other has ever thus enraptured me or will ever do so again." So committed Boltzmannian to the end, okay? And so when you think about Schrödinger, you think about his allegiance as actually being not with quantum mechanics and it's all its bizarre, seemingly bizarre phenomena, but actually with good old-fashioned Austrian statistical mechanics as represented by Boltzmann, Exner, and Hasselhoff. Okay, and so what I think he's up to when he's looking at life, he's actually turning to biology because he was hoping to find in life a means to salvage this deterministic and mechanicist worldview of classical physics that had become undermined by the Copenhagen interpretation of quantum mechanics. I think this is what's going on. And I think the reason why no one has noticed this before is that you only have two kinds of people talking about what is life. You have biologists who know or have little interest in physics, so they don't notice this part, or physicists who have little interest in biology. So I think it's important to look at the whole picture, a whole picture of Schrödinger's work to understand why he was interested in developing these arguments in the context of biology. Okay, so this is what I think we should take from the origin story that I am advancing. Okay, well, the first thing is that he actually decided his answer to what is life a decade in advance. I know there's this paper. Okay, it was never published as an abstract. Can't really see it. It's Why Are the Atoms So Small, which is one of the sections of the first chapter of What is Life. It was delivered to the Prussian Academy of Sciences in 1933. Okay, there's an abstract published. And you know, already in 1933, okay, a decade before, Schrödinger is talking about this distinction between order from order and order from disorder. Okay, what I found looking at the archives is that essentially when Schrödinger came to prepare his lectures on What is Life, he only read the literature that would provide confirmation of the view that he already had to begin with. It's not like he said, let's have a look at what the geneticists are saying and find out what I can say, but rather, which geneticists do I need to read to end up with this deterministic view of nature and of life, okay? The critics are right to say that What is Life is not representative of the biology of the time. You know, Perutz and Pauling complaining about Schrödinger, they're right, but I think that's fine because Schrödinger was never interested in advancing scientific debates in biology. His interest actually was, as I say, in defending this deterministic worldview, because the view that he's giving us of life is an extremely deterministic one, okay? And that's where the idea of new laws of physics comes in, by the way. That's something we can talk about in the Q&A if you're interested, okay? So yeah, the other thing that I found in the archives and the correspondence is that a key motivation that many of the Copenhagen interpretation, the advocates of Copenhagen interpretation have is to actually provide a foundation to use the indeterminacy of quantum mechanics to provide a foundation for the so-called creativity or purposiveness of living systems and also free will in psychology. Okay, so already in the 1930s, you have physicists, Bohr himself, Life and Life, Pascal Jordan also writing in this way. And this is exactly what really got Schrödinger really animated, okay? So, and that's why he has this epilogue, okay, that people have very often sort of derided because it seems completely off the wall. If you read the epilogue, it's only 3 pages. He actually has this, which is very, very telling. It says, to the physicist, I wish to emphasize that in my opinion, and contrary to the opinion upheld in some quarters, we are referring to his contemporaries like Bohr and Jordan, quantum indeterminacy plays no biological relevant role in the activity of the organism. You still need quantum mechanics to explain the covalent bond that is at the heart of the aperiodic crystal. So quantum mechanics is important in that way, but it's a deterministic use of quantum mechanics. There's no room for indeterminacy or any bizarre superposition or decoherence or tunneling or anything like this in biology. There's no room for that, for sure. Okay, this is of course lost by the readers. Even people like Haldane, prefer to mock the epilogue than to take it seriously. He says, this is from the review in Nature of Haldane, by Haldane of Schrödinger's book. A mechanist must either give a mechanist account of life or turn a somersault. In his epilogue, Schrödinger does the latter, somersault, with very great evidence. Okay, so basically no relevance. It's just a somersault in argument. Okay. So we go back now to this is coming now to the end. So I want to go back now to these 2 criticisms. Okay, and let's have a look at them. Knowing now what Schrödinger was up to, let's have a look at why it is that Schrödinger ended up deciding to defend a genocentric view and why he ended up deciding that we should not take stochasticity seriously. Okay, so what I want to say is that this genocentric view that pervades biological view, Schrödinger's biological views, it actually wasn't the orthodox, it wasn't the only view, and it wasn't even the orthodox view among geneticists at the time. Okay, it doesn't reflect what geneticists were saying in 1930s. It reflects what Schrödinger was reading in 1930s. Okay, there's a little tale here of correspondence where I found that he had written to Karl and Hans Sibram. These are a physicist and biologist based in Vienna, where he writes as early as 1932 to ask them for references about grounding motion and the nature of the gene. And then, the brothers respond that, Schrödinger, have you seen this new paper by Pascal Jordan? This is the paper 1932 called Quantum Mechanics and the Problems of Biology and Psychology, where Jordan argued that indeterminacy and free will were based in quantum mechanics. Isn't this terrible? Yes, it is, right? And they basically agree that something has to be done. Someone has to respond. My brother and I are this is a quote from the letter, are very pleased to have you as a confederate in the struggle against occult forces, to use quantum mechanics in this way. And so they say, why don't you read Muller, for example? The gene is the basis of life, seems to provide a solid foundation for this deterministic view that Schrödinger can then defend. And that's exactly what he does, because if you look at the paper in the archives in Vienna, I actually find the notebook, Warum is the name of the title, and in the notebook, there was a little notice here with papers written by hand that Schrödinger was taught or told to read in preparation for the lecture. You can't see this, but I promise you that the last one here is Muller's gene is the basis of life. Okay, so Schrödinger is reading Muller because he wants to, he finds in Muller an ally in wanting to defend this view. Okay, this is a quote from that very famous paper, The Gene is the Basis of Life. You got this very gene-centric view, okay, that then became important in molecular biology. Already in 1929, in Muller, you got this view, and this is what Schrödinger is really paying attention to. Okay. All right, so but what about the book? Because Muller is not mentioned in the book. Who is the scientist that is mentioned more than anyone else in the book? Well, of course, it's Max Delbruck, right? If you think about it, half of the book actually is a discussion of Delbruck's ideas that he presented in 1935 in this so-called very famous three-man paper published with Timoszew Wysocki and Carl Zimmer. Okay, and actually much of the book was actually working out the implications of this model of the gene that Delbruck had provided. In fact, the fifth chapter is called Delbruck's model discussed and tested. Okay, so much of the, and in fact, some commentators have been particularly mean to Schrödinger, like Perutz actually argued the only merit, right, of What is Life is that it popularized the views of this three-man paper, which was published in German in an obscure journal, and not many people read it. Okay, in fact, most people through Schrödinger. I don't know if that's the case. But many actually have actually said this. Okay, and what's interesting about that is that Schrödinger misrepresented to some extent the conclusions of the three-man paper. So this is kind of interesting. Okay, this is a big quote. I'm not going to read it. No worries. This is a quote from the book, from the paper. It's the penultimate paragraph in the paper. Okay, conclusion, and they're saying. He says, this is Delbruck, according to the conception of many biologists, the genome is a highly complicated chemical physical structure consisting of specific chemical pieces of matter. The individual, some attempts have been made to project back theoretically from individual genes to the organism. Okay, so essentially we can start from genes. If you want to understand what organisms are made of, we can theoretically sort of project back to genes as a starting point. Okay, and we can even think of themselves as the ultimate units of life, which is of course a direct reference to Muller. That's the view that you find in Schrödinger's book, but it's not actually the view of the authors. Okay, it's the view that they are actually about to criticize, because the final paragraph, the one that comes just after that, begins. Ideas about the gene challenge this picture, the picture that I've just quoted. Genes, yes, are physical chemical units, but they're likely incapable of directly forming the morphogenic substance, but likely incapable of directing development. They can also hardly be thought of the starting points of development. Therefore, we need not dissolve the cell into genes. Okay, so this is very, very interesting. Okay, and this has been lost. Not many people have noticed this. In fact, the only historian known to show this is Phil Sloan in a book that he published called The Three-Man Paper and Early Molecular Biology, where he translated the three-man paper to basically show everyone, hey guys, we've been wrong about this paper for 75 years because we took Schrödinger at his word. And actually, this is what they were saying. Okay, which actually explains why it is that Delbruck was not really a reductionist. Delbruck has much more in common with the physical views of Bohr than he does with Schrödinger, right? So it's a very, very interesting thing that has been lost because people haven't actually bothered to look at the original text, which was in German and only available, it's very recently not available in English. Okay. So that's all I will say, and I would just want to finish up here. So very quickly, something about the dismissal of stochasticity. Now, you may be thinking, well, surely this is unfair, right? That Schrödinger does not take seriously the idea of stochasticity because it's a fairly, it's a new idea. Well, it's not a new idea, right? Brownian motion is named Brown, who's a Scottish botanist working in the 1840s. It's actually the guy who discovered the cell nucleus. Okay. He named it because he saw pollen grains moving stochastically through a microscope. And we've known for a long time, okay, that at the molecular scale, you can't have deterministic events. You can only proceed statistically because you've got stochasticity at the heart, unless you are absolute zero, okay? A good example here is Darcy Thompson, right? Writing in 1917. and then in the second edition, 1942, before Schrödinger was life, he's writing about, the world of the bacillus, the bacteria, and he says, well, when you take bacteria seriously, you have to forget about gravity. You need to think about the viscosity of the liquid. You need to think about, Brownian movement being fundamental, right? It's determining the physical environment. The world which we have come to the edge of a world which we have no experience and where all our preconceptions must be recast. Basically saying, anyone who's going to be concerned with a microscopic scale cannot project intuitions from the macroscopic world of how physical forces operate, because they're not going to work. Okay. A more telling example is Delbruck himself in his review of what is life in the body of biology. Okay, he says he's reviewing Schrödinger's argument, and he actually says the problem of how the cell gets around statistical fluctuations is never really addressed. The careful reader will be disappointed by this solution. There weren't many careful readers, so no one was disappointed. But basically, Delbruck is noticing already when he read the book that Schrödinger is not giving us a story of how the cell overcomes stochasticity, which is exactly. And so what I'm trying to say is that this is not something that we can only know now with the benefit of 75 years of hindsight. These were things that were noticed at the time by people reading the book at the time. Okay. And with that, I end. And thank you. You've been very patient. Just want to finish very quickly. So what can we conclude then about the book? Well, it is undeniable that the book did intensify the focus on the molecular basis of heredity, which is, of course, the orthodox received view. But we should remember that the book really isn't about the gene. The book is not really trying to tell you about the gene. It's actually trying to tell you about the nature of order. What is the nature of order when you look at life compared to the nature of order in physical systems? Okay. This is one of the hypotheses that suggested that the belief he had that biological macromolecules have to be extremely rigid and stable in order to withstand the disruptive effects of thermal agitation prompted researchers to develop these highly idealized models of studying the process, which I've shown you, right? These circuit diagrams, highly idealized models, making them less disposed to explore how the cell actually harnesses noise to generate order, which is exactly, by the way, what increasingly cell and molecular biologists are interested in, right? How is it that we recognize the gene expression is stochastic, right? We're no longer resisting that idea. So it's become part of how we increasingly think about the cell. Okay. I've also suggested that what is life was not aimed at advancing biology; it should actually be understood as Schrödinger's last wistful attempt to salvage this classical physics worldview that had been undermined by the advent of quantum mechanics. If Schrödinger had given a different view, answer to what it's like, maybe would have had a different sort of development in molecular biology. This is sort of a controversial claim, but the one that we could think about, counterfactually, what would have happened if Schrödinger had defended this indeterminacy, right? Or would we have had a sort of quantum, by the way, seems to be emerging today? And finally, it may turn out this is sort of a paradoxical conclusion that one of the greatest physicists of the 20th century might have contributed to convincing molecular biologists to forget about the importance of physics, meaning the importance of the physics of the microscale when confronting the phenomena of this time. And I'll leave it there. Thanks very much. I'll be very patient.
Thank you very much, Dan. If you have any questions, I would love to address it to Dan. So what brought you to this book?
Well, as I say, I noticed the 75th anniversary of the publication, which was 2018, and I was trying to work out why it is that molecular biologists are so enamored with machine and engineering metaphors, and I was trying to understand what is the origin of that sort of tendency, that they're more comfortable thinking in those terms than they are thinking about, the models of statistical mechanics or condensed matter physics or complexity theory. Okay, and I thought that maybe history could help us understand why it is that molecular biologists feel more at home using particular ideas and where those come from. Right? Of course, you can trace it all the way back to Descartes in the 17th century, Descartes thinking about animals as machines, but there's a more proximate cause that has to do with this book that everyone recognizes as having been an important influence. Yeah.
So if we have no more questions, we also have left, fruits and cookies and everything else. And if you have questions later, you can probably email Dan, right?
I'll be very happy to talk about any of this.
Could you just
yes,
talk a little bit about harnessing noise to generate order?
Right.
What the sort of current view on that?
I mean, I'm not a scientist, I'm speaking as an observer, but I have tried to acquaint myself with the literature on, for example, gene expression or directed transport. So you had traditionally this sort of parastroke model of intracellular transport, the kinase molecules, right? Often even called motor proteins, right? Very mechanical. And yet, increasingly, there's a tendency to think about that movement as being a consequence of Brownian ratchet processes, where you've got this harnessing of two disorderly processes. So you have basically what happened. The model suggests that the hydrolysis of ATP induces a conformational change in the motor protein, okay, which makes it more likely to move in a particular direction. And so you have a sort of order-form disorder. What's possible in life, by the way, seems to be what many biologists increasingly think is the way to go to understand certain biological processes. Another example could be this new emphasis on condensates, liquid-liquid phase separation. I mean, these seems to be phenomena that are not easily understood in terms of classical mechanics. We actually need a new physics to make sense of them, right? So, noise has actually, the very term noise, right? It seems to have a negative connotation. Noise, nuisance, right? It's an engineering notion. And if you look at the literature in the 80s and early 90s, this is the way molecular biologists talk about it too. But it's not the way molecular biologists talk about it now, right? Increasingly, the more you have people talking about the cell using or harnessing the noise rather than finding ways to avoid it, right? And how bacterial populations, use it to bed hedging, processes when they divide. And yeah, so it seems to me, at least, that in a number of different areas of molecular biology, you could even talk about intrinsically disordered proteins as another example, right? Intrinsically disordered proteins don't have a specific functional conformation. They seem to rely on opportunistic interactions with whoever binding partners they find themselves close to. And so the only way you're going to get order there is statistically, right? You're going to expect that the cell is able to perform its functions, the things it needs to do to stay alive, simply because it's likely, right? One hopes that the right reactions or the right interactions will take place. But this is a statistical consideration. It's not one that's coming from some sort of genetic design, a blueprint idea, which was quite common in molecular biology until not that long ago. So I'm trying to talk about this shift from a mechanistic, deterministic engineering view, where you've got this design in the genes that is, and basically you only need to look at the genes. And this is the sort of the view I take to be the classic molecular biology view, to the view that we're increasingly finding ourselves today, where order is something that emerges through, self-organizing processes. The Golgi apparatus, for example, seems to self-organizing. You've got, as I say, crazy states of physical matter, like these condensates that are also responsible for regulation. And so the story is much more complicated, right, than just having this genetic blueprint. Yeah.
I'm just struck by this idea that, getting around the second law is some kind of unique property of living systems, because by this standard, the air conditioning in this building is alive.
By what standard?
I mean, by getting around the second law.
And you think that
our air conditioner gets around the second law very well.
Well, I mean, there's a discussion about whether Schrödinger was the first person, so historical question about whether he was the first person to make this point that organisms actually are not conflicting; they comply with the second law. But that's actually not the case. You have a number of biochemists, and already in the 1920s, talking about dynamic equilibrium and about open systems. Okay, you've got open system, Ludwig von Bertalanffy, right? So it's before, right? So it's, I think, inappropriate. I'm very happy to credit Schrödinger with many things, but I think we should also be careful not to credit him with too many. The discussion of thermodynamics seems to be very inspiring to many people, and yet, as I showed in my talk, it's a very small part of the book, and it's not really connected to the argument about order. He talks about metabolism, right, and there's a stream of order, but he says he doesn't connect it to the aperiodic crystal. Okay, and look at the letter I showed you, Francis Crick writing to Schrödinger saying it's the aperiodic crystal that's going to be super momentous, not the arguments on thermodynamics. Right? So yeah, it's there in the book, but doesn't seem to have exerted that an important influence. Only later, interestingly enough, I don't want to go on about this, but if you look at people who want to legitimize the field of non-equilibrium thermodynamics, okay, and the importance of biological thermodynamics, you know what they do? They use Schrödinger. Say, well, Schrödinger talked about this, so they're using him again as the founding father, just like molecular biologists do. The same thing, right? So, and historians again can come in and say, well, is it right to call him the founding father? He wasn't the first person to make this point that there is no contradiction with the second law because entropy is increasing, because the organism is only maintaining its order at the expense of its environment. So yeah, thanks.
Profoundly disagree with your last conclusion. Says that several generations of electrolysis forgot about the importance of physical forces. The dominant person was Linus Pauling from the beginning, and he really helped develop the concept of the hydrogen bomb. And it was the hydrogen bomb which held together the AT and GCD. So if Kirk and I and Linus Pauling were not molecular biologists, what were we? I think this is just crap.
Okay. Well, I can
only this sentence.
I can explain what I mean here. Maybe we'll see. I don't mean hydrogen bomb. What I'm talking about here is the physical environment that exists at the molecular scale. Okay, it's an environment where
that was too complicated to think about. That's why we did.
Fine, that's all good. But what I'm trying to say is that because it was complicated, it wasn't thought about, and only now are we beginning to realize that it's.
We haven't got very far.
We haven't got very far.
I don't think.
Okay.
I think the great hero remains Linus Pauling.
So there.
Yeah. Well, thank you.
So you see the term quantum biology, like cropping up again and again in the literature and there, and yet there's very little sort of growth in the field. I mean, I see like references like photosynthesis.
Photosynthesis, bird migration, there's a couple of examples.
So it's the reason that given that quantum physics has been around for like since 20s and 20s, more than 100 years, and obviously the biology field itself, that there has been very little sort of this integration of the two concepts, and
there's been very little, you said?
Integration of the idea of the quantum mechanics in biology, not at a practical research level.
Yeah, it was one of the things I actually hoped to find when I came here as a Sydney Brenner Fellow. I was hoping to find if there was any reference to quantum mechanics in the writings of Watson and many others. And actually, there isn't any. I mean, it seems to be clear. My understanding is that it seems to be completely irrelevant. You can understand the molecular basis of life without thinking about quantum mechanics, other than understanding how quantum mechanics explain the covalent bond, right? What I was trying to show here in the talk is that there were physicists like Pascal Jordan, student of Bohr, who actually coined the term quantum biology in 1927 already, okay, who actually thought that organisms act as amplifiers of quantum effects, and that the indeterminacy that you find when you look at microscopic behavior is a consequence of quantum effects. Now, this was completely speculative. He had no mechanism, okay, and it was forgotten, also because Jordan was a Nazi, and that didn't help rehabilitate his views after the Second World War. But what's really interesting is that now, 70 years later, you get people again talking about quantum biology, right? Mentioning Schrödinger rather than Jordan, which is kind of odd to me, because what Schrödinger did in What is Life is actually to show that quantum indeterminacy plays no role. He actually says it, right? So it's a very wrong sort of attribution to want to say that Schrödinger is at the heart of this new quantum biology, right? So yeah, it remains speculative, and maybe you need to tell me, I mean, how respected this kind of work is, or how seriously it's taken. These hypotheses, for example, this quantum tunneling in photosynthesis. I mean, it's
so that kind of like picks up another place where I think like you brought up Roger Penrose.
Yeah.
So he's written about consciousness and like quantum origins of quantum consciousness, like to the tubulins in the cell, which is also responsible for anesthesia and things like that.
Yeah.
So that's like another place where it's like trying to connect. Obviously, it's a very early stage, but it's like anybody you see, it's still in early stage.
Absolutely. And
I wonder if it's just like a wishful thinking or.
Absolutely, and I think that's right. I mean, it's speculative, right?
Yeah.
It's just that what's interesting is that these are really old ideas. Okay, so the idea is that there may be quantum effects in biology is really old. I mean, it predates molecular biology. Quantum biology is older than molecular biology, and yet it's molecular biology that that really exerted this profound revolutionary effect on biology. Quantum biology remains sort of a target of ridicule. Maybe this is how not to do biology, right? I wonder whether that will still be the case in half a century from now. That's something that I don't know.
Some of us will know.
Yeah, it is really like a
To that
difficult
point.
bridge to connect from chemistry, quantum chemistry to obviously, which is
Yeah.
entirely quantum to a like a more deterministic biology.
Do you think that will happen?
No, there has to be an underlying origin to bridge. It's just that bridge has been very difficult to build.
But you don't expect amplification of indeterminate effects, for example, at the biological level. That we can say, that actually has a root in some quantum effect, which is, I think, what the quantum biology people are trying to suggest.
You know what, we can continue talking and drinking. I think it will be a good idea, right?
Okay.
Thank you very much for coming. Thank you. Jackie. It's a really- Yes, I think it is not even more.
I can't wait to see the book.
Oh, thank you very much. And you know, it's all feedback is
We
good
still
feedback.
have
So I
to
appreciate it.
I had put something I thought we were doing.
Yeah, nice to see you, Al.
Yes.
There are a lot of things to think about.
Absolutely, yeah, we could only just scratch the surface. But thank you so
It's
much.
coming out
for
in a
coming.
year.
Yes, exactly.
Wonderful.
Thank you very much.
Just your last
Yeah,
paragraph, right? Because
I understand what you're saying.